Section: Introduction. In this section, we discuss recent advancements in large language models, LLMs, that have expanded their capabilities and the challenges in evaluating their performance. Current benchmarks may not fully capture the complexity of LLMs, especially in real-world tasks aligning with human preferences. To evaluate LLMs, benchmarks are categorized based on question source, static or live, and evaluation metric, ground truth or human preference, resulting in 4 categories. While static, ground truth-based evaluations are common due to their cost-effectiveness and reproducibility, they have limitations such as lack of open-ended questions and static test sets that can become outdated. Establishing definitive ground truth for complex tasks is also challenging. Therefore, there is a need for an open, live evaluation platform based on human preference to better assess LLMs in real-world scenarios. Creating such a platform involves challenges like collecting diverse user questions, developing efficient ranking systems, and ensuring quality human evaluations. We introduce Chatbot Arena, a benchmarking platform where users can ask questions and vote on responses from 2 anonymous LLMs. This crowdsourced approach gathers fresh user prompts and uses statistical techniques to estimate model rankings reliably and efficiently. Our platform has collected diverse user-generated questions and received consistent votes compared to expert evaluations. We have engaged over 90,000 users in multiple languages and provided access to over 50 models from top developers. By updating the leaderboard regularly and sharing information, our platform has become a reference in the LLM field. We are committed to open sourcing our data and code, making our platform accessible to all. Our contributions include building a large-scale live LLM evaluation platform, analyzing collected data, releasing a human preference dataset, and designing an efficient sampling algorithm. Section Summary. In this section, we introduce the challenges in evaluating large language models, LLMs, due to the limitations of current benchmarks, which often lack open-ended questions and can become contaminated over time. To address these issues, we propose Chatbot Arena, a live evaluation platform based on human preference that features anonymous battles between LLMs in a crowdsourced setting. By collecting diverse user questions and leveraging statistical techniques, we aim to provide a reliable and efficient benchmark that mirrors real-world LLM applications. Section: Human Preference Data Collection. In this section, we discuss our interface design for collecting human preferences and share summary statistics. We aim to make it easy for users to provide feedback on models through the Chatbot Arena interface. Instead of using a fixed grading system, we use a pairwise comparison approach where users compare 2 model responses and choose the better one. This method encourages user engagement and diversity in data collection. Users can input any prompt for the models, and after receiving the answers, they vote for their preferred one. If they can't decide at first, they can continue chatting until they make a choice. We also provide options for users who are unsure. Before using our service, users must agree to our terms of use, allowing us to make the data public. We started collecting data in April 2023 and have gathered around 240,000 votes from over 90,000 users by January 2024. Our data includes feedback on more than 50 models, covering various languages with English being the most common. Each data point consists of conversations between users and 2 models, along with a vote indicating the preferred model. We present these statistics in a table along with other human preference datasets. We focus on certain model pairs to reduce the number of votes needed for stable results. We also implement measures for anonymity and content safety. Our data primarily consists of pairwise model comparisons. We aim to use this data to establish rankings for all models. We introduce a sequential setting where users compare model pairs, and we observe their preferences. Our goal is to estimate the win matrix, representing the likelihood of a model winning in a pair comparison. We use the Bradley-Terry model to estimate model win rates and determine rankings. Previous versions of our interface used different ranking scores, such as the Elo score, but we switched to the Bradley-Terry coefficients for better statistical estimation. Section Summary. In this section, we design an interface called Chatbot Arena to collect human preferences efficiently by using pairwise comparisons instead of absolute scores. By allowing users to compare two model responses and vote for the preferred one, we aim to reduce friction and encourage diverse user engagement. Our data collection efforts have garnered over 240,000 votes from 90,000 users, covering more than 50 models in various languages, with an average of 8,000 votes per model, and we employ adaptive sampling methods to efficiently rank models based on user preferences. Section: Efficient Approximate Ranking. In this section, we described how we calculate the win matrix, score, and rank. Now we will explain our estimation procedures. To estimate the win matrix, we define a quantity called x_t, A, which is calculated as the inverse of the probability of sampling pair A at time t, multiplied by an indicator function. This helps us create an estimator for the win matrix. It's important to note that the expected value of x_t, A, is equal to the true parameter we are trying to estimate, denoted as theta_A. Therefore, our estimator, theta_t, is unbiased. We also estimate the covariance matrix using certain conditions and construct confidence intervals based on these estimations. For estimating the BT scores, we use a maximum likelihood estimation approach on our data points, with a focus on achieving a uniform distribution over the actions. We then compute confidence intervals using two different strategies: the pivot bootstrap and the sandwich robust standard errors. Based on our simulation study results, we opt for the sandwich intervals due to their smaller size in larger samples. In terms of approximate rankings, we provide a ranking for each model that considers the uncertainty in the score estimation. By defining a confidence set, we can extract an approximate ranking that ensures no model's performance is understated with high probability. To ensure that no model's performance is overstated, we construct a uniform confidence set using the central limit theorem and the sandwich estimate of the variance. Additionally, we introduce an active sampling rule for detecting anomalous users, specifically anomalous IP addresses in our dataset. By comparing the distribution of ratings for a new user to historical ratings for a given action, we can identify anomalous users using statistical tests and corrections. Despite the heuristic nature of this procedure, it has shown promising results in our initial tests. Section Summary. In this section, we detailed the process of efficiently approximating rankings by estimating the win matrix and BT scores. We described the estimation procedures for the win matrix and BT coefficients, including constructing confidence intervals based on regularity conditions and employing reweighted maximum likelihood estimation. Additionally, we introduced an active sampling rule for detecting anomalous users by comparing their ratings to historical distributions and sequentially testing for anomalies using Fisher's combination test and Bonferroni correction. Section: Data Analysis. In this section, we examine whether Arena's crowdsourced data reflects real-world use cases by conducting topic modeling on the user prompts. We assess the effectiveness of these prompts in distinguishing models and validate the vote quality by relabeling data with experts. To study the diversity of prompts, we use a topic modeling pipeline with BER topic. We convert user prompts into representation vectors using OpenAI's text embedding model and reduce the dimensionality with UMAP. Then, we employ HDBSCAN for clustering and GPT-4 Turbo for topic summarization. The analysis reveals 600 clusters covering various topics like poetry, coding, math, and medical queries. The largest cluster represents only 1% of the set, indicating a diverse distribution. We investigate if Arena prompts can differentiate model strengths. By comparing the performance of Llama 2 to 70B Chat and GPT-4 on different topic clusters, we find that GPT-4 excels in clusters requiring coding and reasoning skills. However, its performance drops in clusters with less problem-solving tasks. This suggests that models have varying strengths across different areas. We demonstrate the quality of prompts by constructing a challenging benchmark using crowdsourced user prompts. By comparing Arena Bench with MT Bench, we observe a significant performance gap between proprietary and open models. Additionally, we validate the vote quality by comparing crowd user, expert, and GPT-4 judge preferences, showing high agreement rates between Arena crowd users and experts. Overall, our experiments confirm the effectiveness of Arena's crowdsourced data in reflecting real-world use cases and differentiating model strengths. Section Summary. In this section, we analyze the data by conducting topic modeling on user prompts to assess if Arena's crowdsourced data reflects real-world use cases. We use BER topic to identify 600 diverse topic clusters, showing a long-tail distribution with small similarities between clusters. Additionally, we evaluate the effectiveness of these prompts in distinguishing model strengths, finding that GPT-4 outperforms Llama 2 to 70B chat in clusters requiring coding and reasoning skills, highlighting the varying strengths of models in different areas within Chatbot Arena. Lastly, we validate the quality of crowdsourced votes by comparing them with expert labels, showing high agreement rates, 72% to 83%, between crowd users and experts, affirming the decent quality of votes in Chatbot Arena. Section: Ranking System. In this section, we present the results of our experiments on approximate ranking. We conducted an experiment where we analyzed T equals 213,576 historical votes from our online platform. We calculated the BT coefficients using our estimation algorithm and determined confidence intervals. These intervals are shown in the figure, both with and without multiplicity correction. The concept of approximate ranking technically requires multiplicity correction, but it leads to wider intervals. To assess the performance of these intervals, we conducted a simulation since it's not feasible to evaluate them directly on real data. We generated a vector of BT coefficients from a specific distribution and created a dataset based on these coefficients. We then calculated the coverage and average width of the intervals for 20 trials. The results, displayed in the figure, show that the coverage of the intervals aligns well with the expected probability, centering around 1 alpha. Moreover, as more models are included, the intervals tend to become larger. Moving on to evaluating our active sampling rule for win matrix estimation, we used the best fit BT coefficients from a holdout set of 213,576 points. We then applied our active sampling algorithm to sample from this distribution. The results, depicted in the figure, indicate a significant improvement. For instance, to estimate a certain parameter with a precision of 0.2, the adaptive sampling method requires fewer samples compared to random sampling. This trend holds for different levels of precision, showcasing the efficiency of our method across various scenarios. In assessing anomalous user detection, we manually identified 25 abnormal users with repetitive or meaningless inputs and randomly selected 25 normal users for comparison. By computing specific values and setting thresholds, we were able to effectively detect anomalous users with high true positive rates. However, some false negatives were observed, mainly from users whose behavior was not consistently abnormal, posing a challenge for detection. Discussing the limitations of our study, we acknowledge the potential bias in our user base, which mainly comprises LLM enthusiasts and researchers. Additionally, the data primarily originates from our online chat interface, possibly not fully representing real-world LLM usage in diverse domains. We also highlight the need to consider safety aspects of LLMs in future evaluations. Looking ahead, we aim to develop comprehensive topic leaderboards and enhance the detection of harmful users using advanced methodologies. Our future work will focus on creating dynamic settings for multimodal and agent-based LLMs to cater to more complex tasks effectively.